this title, greedy algorithm for stochastic matching is a two approximation. You know exactly what you get. This is by Marek Adamczyk. It's Polish. I don't know how to pronounce that. 2011. So the stochastic matching problem was first introduced in 2009. So this is like 2 years after. Right. So we can give them what is stochastic matching. Maybe we've talked about it before in this group, but I'll give a definition. So we're given an undirected graph, and along with this, every edge gets some probability. And roughly speaking, this is like the probability it's existing. So PE between 0 and 1. And additionally, every vertex gets a patience value. And this is how many times we're allowed to essentially check if an edge exists next to it. So I'll kind of formalize what that means. But right. So we can give an example. We have a graph like this. So note the graph doesn't have to be bipartite. It's just any graph. So each vertex gets a patience value, and each edge gets a probability. And what we do in an iteration is we choose an edge and we probe it. And when we probe it with probability PE, it will exist, and then we're forced to add it to our matching. And with 1 minus PE, it doesn't exist and it just disappears. So we can't probe it again. And the patience values of its endpoints goes down by 1 because we used up one of their probes. So there's a few applications of this, quite a few.
You can only probe it if its endpoints have positive patience values.
Yeah, we can only probe an edge if its endpoints are positive, have positive patience values. Yeah, and we of course we can't probe an edge if we already have something in our matching adjacent to it, because then if the probe is successful, we wouldn't have a match. Right. Yeah, so the paper talks about a couple applications of it. It talks about kidney matching and online dating. My application I came up with is maybe I am running a university and I want to encourage collaboration. So each of these are researchers, and I can think for any pair, what's the probability that it will work out, they'll produce something nice. So maybe with Jacob and I, we have this. I'm not very patient. I only will try once. Jacob has a bit more patience than me. And we like some similar things and we work well together, so there's a good probability of working out. But maybe this edge is with my roommate who does mathematical biology, which I don't really know much about. So it's 50-50 that actually pans out. Right, and then the goal would be to maximize the number of edges you select. So in this example, the number of kind of research relationships that work out. Right. So this is a special case.
Do they mention the weighted case at all, or just unweighted?
Yeah, good question. This is unweighted. And in the weighted case, greedy is like arbitrarily bad.
Right.
So there are like approximations for the weighted case, but they use different techniques than greedy. So we're only going to consider unweighted. We're trying to, so our goal is to maximize the expected cardinality of our match. Right. So this is a special case of something we saw a few weeks ago. There was a paper presented, a probing problem. This is exactly a probing problem. It has an inner constraint and an outer constraint. So the inner constraint is for edges that we actually select. So the inner constraint is just matching. And the outer constraint, these are for edges that we're allowed to probe, and these are according to the patience values. Each of these are two systems, right? Any kind of maximal independent set according to these will be at worst half the size of the optimal. So as kind of a corollary of something we saw previously, we get a 4 approximation immediately. So corollary. If you weren't there for the talk, it doesn't matter. I'm just kind of placing it maybe in as we've already seen, I won't actually use any results from that talk. So the corollary is that greedy is a 4 approximation. So we know it's at worst of 4, and we can talk about a lower bound for how good greedy is. If we have a graph like this, and this is not really even a stochastic matching instance, we're going to give each edge a probability of 1 existing, and we can just put patience values of 1 or any number of these. The optimal algorithm is going to select these 2. So opt is 2. And greedy, I should state the greedy condition, just to be explicit. What greedy does is it selects the highest probability edge that's available at any moment. And if there's multiple, it can choose whichever one it wants. So here, we might choose the middle edge, and then we're done. Because it exists, and we can't get anything else. So the optimal is 2, and we only get 1. So it's no better than 2. Right. But yeah, there is a gap here. This 4 approximation, this was shown in a way more general case in the previous talk. It was also shown specifically for stochastic matching earlier in 2009 when the problem was introduced. But yeah, so there was a gap then for a couple of years. But it turns out that this lower bound is kind of the right answer. We can hit exactly 2. So before we get into the analysis, I'll just kind of give some preliminaries on kind of notation and what we're going to look at. So what defines an instance of a problem? An instance of a problem, we're given a graph, we're given the probabilities, and we're given the patience values. As we kind of probe edges, the probabilities on the edges don't change, so we'll just write GET and we'll assume that probabilities are kind of encoded. Right, so where G, as we said before, is an undirected graph, and T is a function from the vertices to the non-negative integers. Because we can't make a patience value negative because we've gone too far. Right. So if we think about how to represent a deterministic algorithm for this, we can represent it as a decision tree, where so we have some deterministic alg. We can represent it with a decision tree T alg, where at the base or the root we have the initial instance, and since we're deterministic, there will be exactly one edge we choose. We can't do a different one, so maybe we choose edge alpha beta. So the probability alpha beta succeeds, and 1 minus the probability it fails. So in the case it succeeds, the instance we get, well, we're not allowed to probe anything next to alpha or beta again because it's part of our matching. So we take the graph without those vertices, and our patience values don't change because the only things we probe next to are now gone from the graph. And on the other side, if the probe fails, well, we remove the edge. So note this is different than this. This is removing 2 vertices. This is removing the edge. And our patience values now change because alpha and beta are still in the graph, but we've lost a bit of patience. So everything is the same except alpha and beta. So yeah, decision tree. And what we'll do is we can think of nodes in the decision tree. So maybe this is node B, right? And then instead of writing P alpha beta, we can just write the probability according to B. And just to avoid confusion, whenever I'm referring to something in the decision tree, I'm going to call it a node. And if I'm referring to something in the original graph, I'm going to call it a vertex. So we don't get confused. Additionally, I'll always use Greek letters for vertices, and non-Greek letters for nodes in the decision tree. Right. Yeah, so any deterministic algorithm can be represented like this, and that includes our greedy algorithm, because it's we assume we have some deterministic tie-breaking mechanism for the edges. Right. Okay, so we can talk further about looking at this tree. So we're going to make a variable. We're going to call it QV. And this is going to be the probability of reaching some node in the decision tree. So, and we can note this is exactly the product of the edge labels on the way down to that node. So that's the decisions that have to work out to reach it. Right, and using these, we can write down kind of the expected performance of the algorithm, and we'll also talk about kind of the expected value for decision trees. The same thing. So this is going to be so for every node in the decision tree, we have a QV probability of getting there, and then it's probably PV the probe at that node succeeds, and so we gain an extra edge node. And just a bit more notation, if we have some vertex V in the tree, or some node V, sorry, we'll call T of V the subtree rooted at V. And L and V and R of V are going to be the left and right subtrees. Right, and finally, in the preliminaries, we're going to assume that there is an optimal algorithm that's deterministic. This is without loss of generality, because the edge probing is not adversarial or anything, so we don't have to hedge. I won't show that, but without loss of generality, ops is deterministic. So then we can represent it with a decision tree, which is pretty necessary. And we also assume it's going to be optimal in all the subtrees. And this isn't technically necessary for an optimal algorithm, because some subtrees might have a probability of 0 of being reached, but it could help in our analysis. And of course, there is an optimal algorithm that's optimal in the subtrees, because if it's probability 0, it doesn't matter what we do. Okay, yeah, so we can get into the analysis now.
So if you are providing positive results, why didn't you make assumptions you're providing? I mean, you're providing not lower bound, but you're providing upper bound. Why are you saying assumption?
Assumptions about the optimal algorithm?
Yeah.
Because I'm comparing against the optimal algorithm, so I'm going to use kind of facts about the tree for the optimal algorithm.
Okay.
Whereas if I can't represent it with the decision tree, it becomes harder to compare against. Right, so we can look at so greedy is of course deterministic, because we assume we have some deterministic tie-breaking rule. So it has a decision tree as well. Right, at the base, we're going to have the original instance, and then there's going to be some edge we probe first, alpha beta. And then we get 2 new instances of the problem. And we'll call them G L greedy and G R greedy. Right. What we want to do is we want to work inductively on this tree. So base case is when there's one edge and then there's only one possible algorithm. So of course it's a two approximation. But we can say that the expected value of greedy on its left subtree is going to be at least half of how opt would behave on the left subtree. Just that's the inductive hypothesis, and we can say the same for the right subtree. And we also have an expression for exactly what the performance of greedy will be here in terms of its left and right subtrees. Right, we have probability alpha beta of going to the left and winning one edge if the probe succeeds. And then with 1 minus p alpha beta, our first probe fails, and then we go to the right. So we'd like to bound this in terms of opt. And we have some bounds here in terms of how opt behaves on the right of the left subtree. The problem is opt may never be run on those. Right? When opt runs, its decision tree could look vastly different from ours. So what our goal is to do is we want to design algorithms that are feasible for the left and another one that's feasible for the right, and compare those to opt. And then using our inductive hypothesis, those are easy to compare to our greedy. So and we want these to be feasible for those instances. And what we'll do is we'll design these kind of based on opt, and we'll see what that means later, but that means it'll be easy to compare to opt. And then by the inductive hypothesis, right, this is at least 1/2 opt, so it's of course at least 1/2 the performance of these things. This would be right. So that's our goal. We want to design algorithms for these instances that we can compare to opt. So we'll start with the right instance. Right. Yeah, so just a reminder of how this is formed on the right. I'll write down now the patient's values as well, because those change. Right, so how's this formed? So first we remove the edge alpha beta that we probed. And then we decrease the patient's of alpha and beta. So by 1. Right, so we need an algorithm that first off doesn't probe alpha beta if it's gone, and has at most t alpha minus 1 probes of alpha and at most t beta minus 1 probes of beta. So we've lost a little bit from the original. Right. And so what we'll do is we'll imagine we're executing opt. So we're given some black box that executes opt. What I mean by that is you give it some instance, GET, and it will tell you what edge to probe. You probe it and you tell it the results, and it will tell you what edge to probe and so on. What we're going to do is we're going to follow the directions it gives us, unless it would break our feasibility. And then we'll fake the probe. So we'll just flip a coin and then we'll lie to the black box. And we'll show we don't lose too much compared to opt. Right, so specifically, we start off by giving the black box the full instance. So not our sub instance, just the full instance, which means it could tell us something that's infeasible. Right, so if we're given the edge alpha beta from the box, we just fake it. And what I mean by fake it is with probability alpha beta, we tell it succeeded, and with 1 minus probability alpha beta, or p alpha beta, we tell it it failed. We don't actually do anything. And the other case where it's bad is if we're given some edge that would be the T alpha probe of alpha or the T beta probe of beta. Everything before that is fine, but that very last one. If it's any other edge, then we're fine. We probe it. And yeah, so after each edge, we either probe it or we fake it, we give it the result, and then we keep following the execution of the black box until we're done. Because of these faked probes, this is feasible for the right instance. Because alpha will get at most T alpha -1 probes, beta will get at most T beta -1 probes, and we'll never probe alpha beta.
Yep. You can check in what is being faked in those cases, because in this case, itself, you can have capacitors when you can fake.
Sorry, can you hear this?
What is it mean to fake?
To fake a probe, it means we don't actually probe the edge. We just like flip a coin. So we get some random bits, and with p alpha probability p alpha beta, we tell the black box that the probe succeeded.
Okay.
And with probability 1 minus p alpha beta, we say it failed. But we don't actually probe anything. We're lying to the box. But because we're rolling it with those probabilities, the box essentially still behaves how opt would, because it's given real probabilities. Yeah. So everyone get what I mean by this algorithm? Okay, good. So now we can talk about the performance. So we can write the expected value of opt. Well, it's going to be the expected value. And when I write expected value of opt or some algorithm without saying the instance, I just mean the full instance. So here, this is running it on GT, this is running it on the right section. So the expected value of opt is the expected value we get from running it on the right subtree, plus this SR term. And this is our loss from faked probes. So for example, if opt tells us to probe alpha beta and we don't, but the probe would have succeeded, we lose 1. So we can write the expected value of SR. There's 2 cases in which we lose something. So it's this one and this one. Right. So the first one is sorry, it's going to be the probability that opt probes alpha beta, and I'll just write that as probe alpha beta. So this is referring to opt. times the probability that that probe succeeds in opt. So if opt probes alpha beta, p alpha beta gains 1, but we gain nothing. Right. And one thing to note is if opt actually probes alpha beta and we fake it, then we're never going to fake any of these. Because we saved one patient's value from faking the probe of alpha beta. We saved 1 on each of them. So any future edges it gives us, we probe. And we don't have to fake again. So this only matters when opt doesn't probe alpha beta. And also we wouldn't have this case before this case because then this would be over the patient's values. So in the case that opt does not probe alpha beta, how much do we lose? So if opt actually takes an edge adjacent to T alpha in the T alpha probe, so that's what this means. In the alpha time, the T alpha time it probes an edge next to alpha, it takes an edge. Well, we didn't probe that, we faked it, so we lose 1. And this is given that it doesn't probe alpha beta, so we can separate this out. And then the same thing for beta. If it takes beta in the T beta probe, we didn't, so we lose 1. Right. So if we combine this and this, we get an expression with opt and algar, and we'll write this down over here. Going to erase this, but I want to keep it for later. So we have that the expected value of opt is less than or equal to, so we have the expected value of algar. And we saw above, now this is feasible on the right subtree, so this is actually less than or equal to 2 times the expected value of greedy on the right subtree. And then plus our error term. So Another. Okay. So for now, we're done looking at the right substrate. We have an algorithm, we have a nice expression for it in terms of opt, which we've then substituted in the performance of greedy with some extras. So we'll look at the left subtree now. Which we'll have to have a different algorithm for because the conditions are different. In fact, the left subtree is kind of much stricter on what you can get away with because we've completely removed the vertices alpha and beta. So instead of making an algorithm that runs kind of using opt as a black box.
So why do you get two times DD over here?
Oh, right, yeah. So here I had originally I had the expected value of algar.
Yeah.
But this is feasible for the right subtree, and so we just use our inductive hypothesis to say this is less than or equal to 2 times the expected value of greedy, because basically on all the subtrees, greedy is a 2 approximation.
Okay. Right.
All right, so yeah, so for the left subtree, we're going to have to make a new algorithm opt prime It's very, very similar to opt, but not quite. And then we'll use that as a black box, and we'll see why in a second. But essentially, what opt prime does is, if it probes alpha beta, it just pretends it was successful no matter what. So I'll say, I'll write down that explicitly. So we're going to let X be the nodes of the optimal tree that correspond to probing alpha beta. Note that none of these nodes are going to be ancestors or descendants of each other, because we can't possibly probe alpha beta and then further down the tree probe. Right, and we're going to define a new algorithm that we'll call opt prime. And what it does is it behaves exactly the same as opt. So just opt on full instance until it reaches a node that corresponds to probing alpha beta. And what it does here is it still is going to probe it. But then it goes to its left subtree and wonder what happens. So even if the probe failed, we just say, oh, it succeeded. So we lose a bit, but it makes it easier to compare later. So it probes alpha beta, and then it goes to the left subtree, regardless of it. Right. So before we analyze this, we're going to need a quick lemma. That lemma is that this is about the optimal tree. So if we have some node V, and the expected value at that node subtree is at most the expected value of the left subtree plus 1. We don't get any proof of this. So the first thing to note is that the expected value of the right subtree is less than or equal to the expected value of the main tree. And this is because a strategy for the right subtree is a valid strategy for the main tree. So if it was better, we would just follow that. And this is the optimal. So that has to be it. Right. And then we can write down what this looks like. This is so probability according to PV, the probe succeeds, and we get a value of 1 from the probe, and we go to the left subtree. And probability 1 minus PV, it fails, and we go to the right. But because of this, you can replace this with just from the tree. And if you rearrange, you get the lemma, and we'll see the steps. But, you just move this to this side, and then you divide out the PV, which is non-zero by assumption. Right. Okay, so now we have the lemma. We'll get another lemma. And that is going to bound the performance of opt prime. So expected value of opt is less than or equal to the expected value of opt prime plus an error term. Which is just this 1 minus P alpha beta times the probability that opt actually probes alpha beta. We can kind of see where this comes from. If opt doesn't probe alpha beta, then of course we lose nothing. And then the higher the probability, yeah, so the lower the probability that it succeeds, the more likely we are going to diverge from what opt does, right? If it always succeeds, then opt prime is exactly opt. If it's quite low, opt is going to go to the right substrate, we go to the left, and it could be quite different. So yeah, so we can write down. All right, okay, so first I'm going to define this T of big X. And this is just going to be a union of these trees rooted at X, for this definition of X. So the trees rooted at places where we probe alpha beta. These are disjoint. This is a disjoint union because you can't, like I said, one can't be a descendant of the other because we can't probe alpha beta twice. Right. So now we can write down expected value of opts. So outside of these trees, it behaves as normal. So it's QV TV term earlier. Probability we get to a vertex times the probability its probe succeeds. And then inside of here, so for all X in big X, it's going to be the probability we get to that node times the expected value of its tree. And now we're going to use the lemma we had previously. We can get rid of this expected value of the tree and say it's less than or equal to 1 plus the expected value of the left subtree there. Get it less than or equal to. We can write down the expected value of prime. So outside of these x's, it behaves exactly the same as opt, because it doesn't diverge until we hit something that probes alpha beta, and then inside it's just going to be probability we get to that node, and then with probability alpha beta the probe succeeds, and then no matter what we go to the left. And if we kind of put it together with some manipulations, we find that the expected value of opt is less than or equal to the expected value of opt prime plus 1 minus p alpha beta times the sum of these qx's. But the sum of qx's, this is exactly the probability that we probe alpha beta. This is the probability we hit a node that probes it. They're all disjoint, so we sum them. And this proves the limit. So yeah, so the error term is not so bad. And now we can design an algorithm for the left subtree. And it's going to be the same as before. Ish, same idea. So we're going to think of opt prime as a black box this time. So the same thing as before, we feed the box kind of the big initial instance, GT. And we want to be feasible for the left subtree. So anytime it gives us an edge that's next to alpha or beta, we have to fake the probe, because we're in the left subtree. That means we took the edge alpha beta into our matching. We can't probe anything next to it. So if we get an edge adjacent to alpha or beta, fake the probe. And this means exactly the same as it did on the right. With probability p alpha beta, we say it succeeded. With probability 1 minus p alpha beta, we say it failed, but we didn't actually probe it. We just told the black box what happened, supposedly. But otherwise, we can probe. Because if it's not adjacent to alpha or beta, it's fine. So we do the same thing. We just follow the execution of black box with just some faked probes. This is feasible for the left subtree because we never probe anything next to alpha or beta. Everything else is the same because the patient's values haven't changed or anything. So yeah, as before, we can write down kind of the expected value of opt prime is equal to the expected value of this algorithm. So this is algal, follows it, plus the expected error term, which we'll call SL. So this is the error just from the fake terms. Right. Here is always the proof of this. Right, so let's talk about the expected error term. So if opt prime tells us to probe the edge alpha beta, well, what happens? With probability p alpha beta, the probe succeeds, like we fake it, we roll p alpha beta, and we're done. It will never probe anything next to alpha or beta again because it thinks it's added to the matching. But what if it fails? So we have this probability 1 minus p alpha beta that we reported it failed. But it still won't probe anything next to alpha or beta again because we defined opt prime in that way. When opt prime probes alpha beta, it just pretends it succeeded, even if we tell it it fails. So that's really nice. If we're told to probe alpha beta, that's the last probe we need to figure out. Right. So I'll write this. It's before probability of probe alpha beta. Actually, no, I can't do that because this is the probability opt prime probes alpha beta. We have to keep that there. So it's not the same. So before, when we wrote probe alpha beta, we're talking about opts, but this is a different algorithm. So, and then we have the probability that opt prime doesn't probe alpha beta. Then there could be other probes we have to pick. So what does this look like? It looks like. So if opt prime ever takes an edge next to alpha, we've lost 1 because we didn't take it since it was definitely a fake probe. And then the same for alpha. So just, or same for beta, sorry. Right, if opt prime takes beta, we definitely fit it. But one thing to notice is, so the probability that opt prime probes alpha beta is exactly the probability opt probes alpha beta, because before we hit alpha beta, we behave the same. So we get rid of the prime here and here, and here. And given that we don't probe alpha beta, then opt prime is behaving exactly the same sign. So we can get rid of it here. So this is still all types of opt. So that's nice. So we have 2 bounds, right? If we combine this statement with this statement with this statement, we have a bound using the left subtree, and we have a bound using the right subtree. And we can put it all together into one huge bound by adding and multiplying. So I'm going to erase all this, but I'll write down the big one right away.
Now you use more borders.
So more words.
I don't know if you want it.
I want to keep that up because like the visual is true. Thank you. So we have a bound for the right one. We'll multiply this entire bound by 1 minus p alpha beta. And we'll take the bound for the left one and multiply the entire thing by p alpha beta. We add them up. On the left, we still have opt, and then on the right, we have a bunch of things multiplied. So first, we have the bound for the left, which is going to be expected value of alg L, which I'll just write as, I'll keep it as alg L. Yeah. And what we had plus the probability we probe alpha beta. Right, yeah, because we had two terms there that. This is because we had two terms. So we had some p alpha beta times the probability we probe alpha beta. And then we also had some 1 minus p alpha beta times the probability we probe alpha beta. One of these was from how we bounded opt prime, and one was from how we bounded SL. So because we had two different sources of error, they combine into one. So just keep that there. So there's a little bit less writing. The rest of the proof is mostly rearranging now. With one important bound. Right. Okay. So that's the entire bound we got from the left. I don't remember where the terms come from. It's not super important, but and then we have the bound from the right, which we wrote over here. We'll put it back in terms of algar for now. And then we had and then yes, and then we have the not probe part. A lot of these terms will add together and cancel. So we have the probability to take alpha and C alpha given we don't probe alpha beta. And then the same thing for beta. Right. So there's some rearranging work to be done. I'll just write out what we get after rearranging. Of course, get p alpha beta times the expected performance on the left, plus 1 minus p alpha beta times the expected performance on the right. And we get sorry, this is the exact equality. And then a really big term that we'll see goes to nothing. So probability to take alpha, given we don't probe alpha beta, plus 1 minus p alpha beta over p alpha beta. So we took out a factor of p alpha beta there. Times the probability we take alpha in the T alpha round. And then this exact same term again, but for beta. Beta, beta, p beta. Right. Yeah, so this big thing is maybe annoying to deal with. So we have a claimed up on the L right here. And that is that entire term is just less than or equal to 1. This is less than or equal to 1. And analogously for beta. We'll prove this claim later, but let's see what it gives us here. We have this is less than or equal to 1, this side. So yeah, take this less than or equal to. We can just erase this. And here we get another p alpha beta times the probability we don't probe alpha beta. So there's 2 of those. We have this minus p alpha beta term here. We can just get rid of it and we still keep an upper bound. So this adds up to, so we have p alpha beta times something plus 1 minus p alpha beta times something, and then these probably probe alpha beta plus probably we don't probe is 1. So we get 2 p alpha beta. And then let's write in kind of from the inductive hypothesis that on the right and left subtrees, we're at a 2 approximation. This is just write greedy on R because I ran out of room there. On left L, sorry. Let's call it R. Right, so we take out a factor of 2, we have p alpha beta times what we get on the left, plus 1 minus p alpha beta times what we get on the right, and an additional p alpha beta, which is the probability we actually get the edge from the first probe. So this is exactly it's exactly 2 times the expected performance of greedy. So given this claim, that's it. Greedy is a 2 approximation. But the interesting thing is we haven't used anything about the greedy algorithm yet. This holds for any algorithm so far. So hopefully in this claim we'll use that that it's greedy, or else we've shown something kind of concerning. Yeah. I'll get rid of this because it's just rearranging. Right, so the claim, we'll prove it indirectly with the lemma that directly implies it. And this says a very important condition, given that p alpha beta is the highest probability of existing edges, then we have that 1 minus p alpha beta over p alpha beta times this probability that we take alpha and C alpha, given that we don't probe alpha beta. So that's this the right side of this equation. We have that this is less than or equal to the probability that opt doesn't take alpha, despite probing it T alpha times. So probing an edge next to it, T alpha times. Given that we don't probe alpha beta. Right, so this is what it shows, but we can immediately tack on an extra thing. This is less than or equal to just the probability that opt doesn't take alpha, given that it doesn't probe alpha beta. Right, because we have this condition despite T alpha probes, but of course it's upper bounded by the probability we're just going to take it. And if we add that with this term, probability take alpha given something plus a probability we don't take it given something, we get 1. So for this lemma immediately implies the right. So we can write out what it means for alpha to take alpha on the T alpha iteration. because each edge can only be taken once, we can just sum over, or sorry, we can only take one edge adjacent to alpha, sorry. We can just sum over all the vertices, or yeah, vertices adjacent to alpha, and get the alpha beta, times the probability that we take that particular edge in the T alpha. So what I'm going to do is I'm going to separate this. So what it means to take alpha gamma in the T alpha round, this means we have to probe it in that round, and it has to succeed. And we can separate this out. I can say it's going to be independent, so I can say this is probability off probes alpha gamma times the probability of the probe succeeds. So we still haven't really gotten anywhere. It's P alpha gamma doesn't help us here. But it does if we do this. So the same as above, but we've replaced this, the P alpha betas with P alpha gammas. And the reason this is true is because if we have a function 1 minus x over x, this is decreasing. So when P alpha beta goes down, then that means it's this is the wrong way, less than or equal to, sorry. Yeah. So when P alpha beta goes down, this will go up. And that's the only place we use that is right. Okay, so then this cancels with this, and we have 1 minus P alpha gamma times this big probability. So 1 minus P alpha gamma is the probability that the probe did not succeed. So we sum over all these probability that we probe alpha gamma on the T alpha iteration and it doesn't succeed. This is exactly equal to that. So probability of doesn't take alpha despite T alpha probes. Even we don't probe alpha beta. And we're done. Yeah. Does anyone have any questions?
Sorry, I thought that for the right hand side, it was, you know, faking it all the time, it was involving alternative.
The right hand side, no, not quite.
No.
We faked it if it's this, in particular, the edge alpha beta, that's
Okay.
gone. But we still allow some probes to alpha or beta, just not the T alpha probe. So like if
Okay.
the patient's of alpha is 5, we'll take the first 4 probes, but we can't do the 5th because we've lost patients.
So it feels like you can take some yeah, I mean the problem is much simpler when you take how do you say this patient's greater than the degree or something vertex, because you can never or I'm struggling with the intuition of it feels like somehow when the patient is large, something happens, or when the patient is small, something else happens.
Right. Yeah. So when the patient's is large, we essentially have no outer constraints, because we can just probe
Yeah.
anything we want. And then the patient's is small. I mean, yeah. So in either case, we still can't do better than 2, just because of the lower bound. We saw at the very start it holds. And of course the analysis still works. And it's small, so every patient's is 1. I guess if every patient's is 1, we wouldn't really have to do anything adaptively, right? We could just kind of select a set of edges we want to probe. Because yeah, the left and right subtrees would be the same, because when we probe something, it succeeds, we remove alpha and beta. And when we don't probe, or when it doesn't succeed, we essentially remove alpha and beta because they're patients with 0. But for like patient size too, I don't know how it changes.
Did it mention about the like adaptivity gap, like if you allow some adaptive policy, can you do, is there a better approximation?
Right, if you have an adaptive policies. They don't. They don't mention that, no.
Greedy is adaptive, right?
Yeah, greedy is adaptive, but could you do better with another algorithm?
It does
They don't
reduce non-adaptive because you like compute this the sequence in advance, like this is the order.
I mean, I thought greedy was like, you prove the maximum probability is that, yeah.
Yeah.
Right.
That depends on what was the realization before.
But like the sequence is the same, like it's always the same order, like you know? No, because
Well, the solid is going to be ineligible.
Maybe you have the same order, but you just skip an edge if it's not.
Yeah.
So I guess in that sense, it's not adaptive.
if you allow like, you can switch the order after this. But they don't,
No, they don't mention any kind of adaptivity gap or even like other approximations. And I tried looking up to see if something better than 2 exists, like non-greedy, but I found some for like the weighted case. Not better than 2, worse than 2, but I didn't find anything for the unweighted case.
You said that the greedy algorithm can be arbitrarily bad in the weighted case.
Yeah.
Is it by greedy algorithm that you mean the algorithm that takes the available edge with the highest value multiplied by the probability of occurring?
So this would be the highest probability edge. If you take the highest value times probability.
Sorry, highest probability is in the weighted setting doesn't make sense, right? I mean, yeah, the weight should.
Right, yeah. I believe even if you take times the weight, it can be arbitrarily bad, but I haven't
That's
seen.
the natural greedy.
Right.
And
I mean, otherwise it's clear that it's always really bad.
is there a simple control?
I don't have one off the top of my head. I didn't look at that too closely.
You know what happens if instead of the patients decreasing by 1, it like decreases by the probability of the edge that is probed.
And then it has to be at least 1 to probe in the future. I don't know what happens.
I don't know.
I
Random
think you could still get a 2 approximation. I'm trying to think of anything that would break. It would be more annoying to analyze for sure.
So,
I didn't think of that, no.
for the weighted case, there is a constant factor.
There is a constant factor approximation, but not greedy. There's like a 1/3 or something. I guess like a 3 would have this condition around there. It's not exact. By the same author, actually, with some other people, but I believe in 2018 published some improved approximations for the weighted case.
and did they mention the use of contention resolution schemes in the weighted case?
I didn't look too closely at the weighted paper, so I just kind of looked at the results. I'm not sure what their techniques are.
Okay.
If you don't know about what benefits you, what, I mean, still. What is the role of this?
For unweighted max
Yeah.
cardinality. I don't know, actually. I didn't see, like, I imagine it's like probably you can't get a p-test, but I didn't see any hardness results when I looked either. It seems maybe it's not too popular to just consider max cardinality, because in most applications there's going to be some weighting.
And for rating?
For weighting, what's the I didn't check. I don't know.
Are there any more questions? Okay, let's thank the speaker again.